Today, we'll be solving LeetCode 133, Clone Graph. In this problem, we are given a node in an undirected graph, and our task is to return a deep copy of the entire graph. A deep copy means that we don't just copy references to the same nodes, instead, we build an entirely new graph where each node and each edge is freshly created. Each node in the graph has two pieces of information. It has a value, which is usually an integer, and it has a list of neighbors, which are the other nodes it is directly connected to. The input is given as a reference to a starting node, and since the graph is connected, we know that from this node, we can eventually reach every other node in the graph. So how should we approach this? Let's think. To clone the graph, we need to visit every node and copy its value and its connections. But here's the tricky part, graphs can have cycles, meaning we might come back to a node we've already seen. If we don't keep track of what we've already cloned, we could fall into infinite recursion or create duplicate nodes. To avoid this, we need a mapping from original nodes to their newly cloned copies. We can solve this problem using depth-first search, or DFS. Starting from the given node, we will check if we have already cloned it. If not, we create a new node with the same value and store it in our mapping. Then, we recursively clone all of its neighbors and connect them to this new node. Eventually, we return the clone of the starting node, which will have the full graph connected through it. Now, let's carefully go through the code step by step. We start by defining a function called cloneGraph that takes in a node. The very first thing we do is check if the node is none. We say if not node, then return none. This is an edge case where the input graph is empty, so the clone is also empty. Next, we create a dictionary called old_to_new. This will map original nodes to their cloned copies. For example, if we visit the original node with value 1, we will store it in this dictionary and map it to the newly created clone of node 1. This way, if we encounter the same node again, we can simply return the clone without rebuilding it. We then define a helper function called DFS that takes in a node. Inside DFS, the first step is to check if the node is already in old_to_new. We say if node in old_to_new, then return old_to_new at node. This means we have already cloned it, so we can reuse that clone. If the node is not already cloned, we create a new node. We say copy equals node of node.val, and we add this to the dictionary by saying old_to_new at node equals copy. This ensures that the original node is now mapped to its clone. Now we need to take care of the neighbors. We loop through each neighbor in node.neighbors. For each neighbor, we call DFS recursively, which will return the clone of that neighbor, and then we append that clone to copy.neighbors. This step is what actually rebuilds the graph connections. Finally, after processing all neighbors, we return the copy. This completes our DFS function. Back in our main function, we simply return DFS of node. This call will trigger the cloning process and eventually give us the cloned graph. In terms of time complexity, this solution runs in O of n, where n is the number of nodes in the graph, because we visit and clone each node once. The space complexity is also O of n due to the recursion stack and the dictionary we use to store our mapping. And that's how you solve LeetCode 133, Clone Graph. Thank you for watching and let's keep learning.